Okay, welcome to part 2 on the video on radicals. We were just about to discuss the idea of the fact that squaring and square roots and in general radicals and their corresponding exponential functions cancel each other, they're inverses. Just to kind of see why that's true, let's take this one, the square root of 3 and then that squared, and see why if I write this as exponents you can see why they cancel, right? Because the square root of 3 is 3 to the 1/2. And if I square that, then that's 3 to the 1/2 times 2, which is 3 to the 1. And what that means is this is 3. Effectively, what happened is the square root and the squaring, they were inverse operations, so they cancel each other's effects off in a sense. But you do have to be kind of careful here, and we'll see some cases why in a second, where there's a kind of caveat that goes with it. Let's do this one. The cube root of -8 cubed, right? So what is this? This is a -8 to the 1/3 power first, and then we're cubing that, right? And so what is that? -8 to the 1/3 cubed, that is -8 to the 1 power, and so that is that's just -8. And so again, effectively, it looks like the cubing and the cube root effectively cancel each other out, which in general that happens, right? But there are some cases where you have to be careful. Let's take a look at this over here. If the exponent if the exponent is on the outside, like this case right here, you're basically okay. That's always going to work, and it's going to always cancel and leave just whatever's inside the radical as the answer, right? The cubing something does cancel the effect of the cube root, and squaring cancels the effect, as long as the exponent's on the outside. But where you have to be careful is if the exponent is on the inside of the radical. In other words, the radical is the outside operation. Because let me write what this is in exponents, right? This is 2 to the 5th first, and then to the 1/5, right? So 2 to the 5th, that turns out to be 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 32. This is 32 to the 1/5 power, and then when I take the 5th root of 32, I get 2 again, right? So this one does result in canceling, right? The 5th root did cancel the 5th power and leave a 2, which is great. But what happens if I do this? What if I have the cube root of -12 cubed? Well, let's try that again. Same thing. We have -12 cubed, and then I'm going to take the 1/3 power of that. So what is -12 cubed? Let's see, that's a -12 multiplied by itself 3 times. So that's -12 times -12 times -12, which is a big number, right? 12 times 12 is 144. Actually, I'm not sure exactly what it is. I'm not going to figure it out. But whatever it is, it's a negative times a negative times a negative, which is a negative number. So it's the negative of 12 cubed, okay? And then I'm taking the cube root of that. And that's okay, because you can take a cube root of a negative and you'll get a negative number. And so again, I'm going to end up with -12, right? Because it was a cube root, and you can take a cube root of a negative, right? And this will result in -12. So again, it looks like the cube and the cube root cancel each other out. But this last case over here, the square root of -12, illustrates why you have to be careful. Okay, what is this saying? It's saying take the -12 first, square it, and then take the raise that to the 1/2 power, take the root of that. So what is -12 squared? Well, that is -12 times another -12, okay, which is positive 144. And if I take the square root of positive 144, I get positive 12. So what happens here? Well, the square root of -12 squared, I got a 12, but it wasn't negative, right? It did not succeed in canceling, right? These did not cancel exactly, right? They did give me the 12, but I lost the negative sign. And the reason I did that was because by having the exponent inside, once I squared that -12, the negative was gone forever, and when I took the square root, it wasn't possible for me to recover that number, okay? So to kind of keep it straight, here's a table that sort of shows you this property written out. It says this: if you have the nth root of a to the n power, okay, in other words, the exponent is on the outside, okay, that will always just leave the a. In other words, the n and the square and the nth root of n cancel, as long as a is a real number, okay? If you have the nth root of a to the n, and this exponent is on the inside, that will also equal a as long as a is positive. If a is positive, there's no negative to lose, so that effectively cancels out, which is good. And as long as n is odd, where you can have, say, a cube root, right, it's okay even if this is negative, right? If a is negative, these will cancel and leave an a. That's okay. But the one case you got to be careful about is if this is if you're taking like a square root or a fourth root or a sixth root where n is an even number, and if this is negative, then you will not effectively get cancellation. The nth root of a to the n will equal the a, but it will be forced to be positive. That's why we write that as the absolute value of a. It seems like a kind of a nitpicky detail, but it is important to be precise. Okay, so in general, the way I'd summarize it is this. An nth root and raising to the n power, they do cancel each other out. And you will always get the number that's on the inside left, right? But the difference is you got to be careful. If you have a negative inside and you have an even power, then you lose the negative sign. All right, next topic. Next topic, how can we use these various rules to simplify radicals? So let's define first what constitutes a simplified radical. A radical is fully simplified when the number under the radical is as small as possible. There's only one radical in the expression. There's no fractions that are inside of a radical. And if you do have a result that's a fraction, there's not a radical in the denominator, although it's fine to have a radical in the numerator. Okay, so there's a lot of times we're asked to simplify radicals, simplify expressions that have square roots or cube roots, something like that. So we're going to take a look at some examples. There's basically two kinds of general ways to do it. One is like for a square root using perfect squares, and the other one is using what we call prime factorization. So I'll do one example of each, and then we'll kind of flip back and forth. To use perfect squares, we're going to use this idea that I could separate this into two square roots that are multiplied together. If I can find two numbers that multiply to 108. Now, it's only valuable if I were to separate something that's a perfect square, okay? For example, here's a list of perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. You know, if I could divide by a number that's on this list, say, for example, the 4, if I can divide 108 by 4, which I can. If I divide 108 by 4, I get 27. So 108 is the same as square root of 4 times square root of 27. And because square root is a perfect square, this 4 here becomes a 2. And now I've simplified because I've written this as something where I have a smaller number in the radical. Okay, so this is 2 times the square root of 27. Now I can simplify even further, right? Because the square root of 27 can be written as 9 times 3. There's another perfect square here. This 27 can be written as a square root of 9 times the square root of 3. And then that square root of 9 becomes a 3. Okay, and then you can now, at the end, you can combine everything that's not in the square root together and everything that's in the square root together. So we get 6 square root of 3. Now this procedure that I just showed here is exactly the way I would recommend that you do this. Work vertically. Start writing underneath, and at every stage, always have the entire expression, but just make a change, right? To go from square root of 108 to this, all we did was separate it into two numbers, but they're still under square roots, right? What I did to go from here to here was I converted the square root of 4 into a 2, and then I copied down the square root of 27. What I did in the next step was I took the square root of 27 and I split that into square root of 9 times square root of 3 underneath the square root signs, and I just copied the 2 because it's still in the expression. And then to go from the next one, I took the square root of 9 and I converted it into a 3. And then the very last step, I combined everything outside. So if you do it this way, right, you won't get confused. I'll see people that start writing numbers, but they just arbitrarily stop writing the square root symbol. And when you do that, it gets very confusing. Okay, so that's one way to simplify. You can try to divide out numbers that are perfect squares. Okay, there's another related way, and some people like this better, and sometimes this is a better solution, called using prime factorization. In this case, you just keep dividing until you can't divide any further, regardless of whether the numbers are perfect squares or not. So maybe you just say this is square root of 2 times, what would that be, 54. And you just keep going here. Square root of 2, if I take 54 and divide by 2, that's 2 times 27. And then square root of 2, square root of 2, this is a 9 times a 3. But the square root of 9 is a square root of 3. times the square root of 3. So you can keep dividing it until you get what's called the prime factorization. 108 is really 2 times 2 times 3 times 3 times 3. Just keep dividing and dividing and just keep copying square roots. But when you're at the end here, every time you have a pair of square roots, like for example the square root of 2 times the square root of 2, well, what is that? That square root of 2 times square root of 2 is a square root of 2 squared, and the square and the square root cancel. So that pair is just a 2, right? And this square root of 3 times the square root of 3 is a 3. And then at the end I have a square root of 3. So the whole thing is 6 times square root of 3. Same as we got the other method. Well, so you can kind of pick which way you like better. Sometimes it seems like prime factorization is a great way to go. It's particularly a good way to go when you do things with variables. But you can also divide out with perfect squares. Okay, let's take a look at an example that has a cube root. Same idea. The only difference is we have to divide out perfect cubes, right? So here's some perfect cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. So if I want to take this approach, I might need to find things on this list, like maybe the 27 to divide out, right? Cube root of 54 is the same as cube root of 27 divided by cube root of 2, because 27 times 2 is 54. Well, the cube root of 27 is 3, because it's some number multiplied by itself 3 times to give 27. That's 3 times 3 times 3. So this one becomes a 3 times the cube root of 2, and that's the simplification of that. A number 3 times a cube root of 2. Okay. Let's simplify this one. Let me give you this one. Let's see. What I like to do is I like to separate first into numbers, x's, and y's. Let's deal with each one separately. I'm going to use that property that I can take things that are multiplied and separate into separate radicals that are multiplied. Okay. Well, you know what I notice here? Let's look at the square root of x squared for a second. What is that? That right there is x squared to the 1/2 power. So would you agree that since that's x to the 1, these effectively are canceling? Whenever I have a square root of an x squared, they cancel, and that leaves me with an x here. Let's take a look at the y for a second here. This is y to the 4th, and then raised to the 1/2 power. So, right, isn't this y to the 4/2? Right, and so that's y squared. So what I want you to notice is a square root just divides the exponent by 2, right? So this is that y to the 4th becomes a y squared. And then for the 80, maybe we do this is 4 times 20, which is 4 times 4 times 5, and the square root of 4 times the square root of 4 is a 4. So I have a 4 times the square root of 5 times an x squared. And all of these things are outside, so I can combine them together. 4 times x times y squared. And then a square root of 5 is the only thing that's inside the square root still. Okay, so that's a good way to do this. Kind of split it off into things, and then think of it as the square root is cutting the exponent in half because it's multiplying by 1/2. Okay, here's another one. I have a square root. What I'm going to do here is, the square root there's no square root of 75, but I could write the 75. Let's split it first into numbers and x's, and then the square root of 25 is square root of 75 is 25 times 3. And what if I took the x cubed and wrote it as the square root of x times the square root of x squared? Right? That x cubed is a square root of x and a square root of x squared, and that's because now I get a cancel here, right? And I do some canceling here, right? So the square root of 25 is a 5. I have a square root of 3. I have a square root of x. But the square root of x squared, by peeling off 2 of those 3 x's, that comes out from underneath the radical because the square root of x squared is x. So I have a 5 and an x that are multiplied on the outside. And then inside the square root, I have a 3 and an x. So that would simplify to 5x times the square root of x. And we would call this fully simplified because we've got the smallest number possible inside the radical. All right. Try this one. What do you think the answer to this one is? Well, if you're using the property that the 4th root and the 4th cancel and leave a 5x, you're correct. Almost. The only thing is, this is the dangerous case, right? This is the one where the root is on the outside, not the exponent, and it's even, which means there's a chance of losing the sign information. In fact, if x is negative, when we take to the 4th power, we're going to lose that. So technically, it's 5 times the absolute value of x, not 5 times x. Okay, let's see, we're almost at the 15-minute time limit here. We'll pick up this one in the next part.